So tonight's speaker, Robert Wills. Robert works as an engineer for Cisco in Harpenden, writing software for the highly reliable routers that form the core of the internet. In his spare time, he has a keen interest in the history of computing and particularly enjoys talking about how computers were actually used and the people involved, as well as the technical side of things. Robert has been fascinated by the Apollo guidance computer for over 10 years and is still learning new things about this extraordinary machine. So, without further ado, can I introduce Robert Wills on the Apollo guidance computer. Thank you, Robert.
July the 20th, 1969. Neil Armstrong and Buzz Aldrin were in the lunar module, 40,000 feet above the moon's surface and descending rapidly. All seemed to be going well when suddenly the onboard computer indicated a 12:02 program alarm and the computer restarted. Neil Armstrong, as ever, remained cool, calm and collected and radioed Houston with just a hint of urgency in his voice, asking for a status on that program alarm. 3 nail-biting seconds later, Houston gave Armstrong the go to continue. Suddenly, another program alarm occurred, and another, and another, and another. In total, during the Apollo 11 landing, 5 program alarms and restarts occurred, the last one just 2,000 feet above the moon's surface. There could not be a worse time in the flight to be having computer problems. At the time, the media gleefully reported how Armstrong seized manual control from a crippled and failing onboard computer and managed to heroically and single-handedly land the spaceship with program alarms flashing all around him. Nothing could be further from the truth. Yes, Neil Armstrong and Buzz Aldrin were brilliant pilots, and their calm and professionalism played a key part in the mission. But the Apollo guidance computer worked flawlessly in this mission and every other mission that it flew. And this was thanks to pioneering hardware and software design principles that were used to make it robust against any failure. In this presentation, I'm going to introduce you to the Apollo guidance computer. Then I'm going to walk you through step by step how they landed on the moon, and I'll show the computer doing that. Next, I'll talk a little bit about how they designed the software to make it robust. And finally, we'll jump back into the cockpit. We'll go through the Apollo 11 landing. We'll get to the bottom of those program alarms. First, a little bit about me. I work for a company called Cisco, and we create a lot of the hardware that runs the internet. And in my spare time, as was already said, I love the history of computing. And I think that these computers should not sit on a shelf and gather dust, but they should be plugged in, switched on, and brought to life. Or, if you don't have an Apollo guidance computer, a spaceship and a spare moon handy, at least give a presentation like this one, really showing things off. And I've been lucky enough to talk about this at the NASA Goddard Space Flight Center, the National Museum of Computing, and various universities. And I am absolutely delighted to be talking to the Mexico Instrument and Astronomical Society, which I did not know existed until I got the invitation. Now, how I could possibly have missed that is just beyond me, but I shall claim that I'm a Southerner and not so wise to these things. And just a note, so I often speak about this to audiences which are quite technical. You know, they have quite a lot of sort of computer background. My screen is frozen. Hopefully people can hear me.
You're back, Clive.
So I often speak about this to people with a very sort of technical background. I'm sure there's actually quite quite a range of people in the audience, but I've tried very hard to make this talk sort of not too technical, and so I hope that there's something here for everyone. Possibly the best test of this is that my mum has watched it, and my mum is the least technical person I know, and she took plenty from it. So I hope that everyone here enjoys it. Okay, without further ado, let me introduce you to the computer. So there it is on the slide. And it was designed at MIT. And it was actually the first contract that NASA awarded as part of the Apollo program. So right at the beginning, they realized they would need some sort of onboard computer. And it's responsible for almost all of the guidance, navigation, and control of the Apollo spacecraft. And on each mission, actually 2 computers flew. So one flew in the command module, that was like the sort of mothership, and then another computer flew in the lunar module, that was the thing that actually landed on the moon. And they had different software on the 2 computers because it needed to do slightly different things. It weighed only 32 kilograms, consumed only 55 watts, that's less than a light bulb, and occupied only 1 cubic foot of space. Now, cast your minds back. This is the 1960s. Most computers filled entire rooms, weighed tons and tons had tons and tons of weight, consumed vast amounts of power. So those 3 numbers on the slides are truly remarkable. And the computer could do about 100,000 instructions per second. So 100,000 sort of simple calculations, which is not very fast, but as you'll see later, you can do a lot with 100,000 instructions per second. Now, most modern day computers, including things that fly on modern satellites, use sort of big integrated circuits that sort of has the whole functionality on one little chip. But back in the 60s, that technology didn't exist. So the computer was built completely from scratch from one type of logic gate. And it had about 5,500 of these logic gates made up the final computer. And those gates were organized into integrated circuits. So you had 2 logic gates per integrated circuit. So in total, about 3,000 integrated circuits made up the computer. And those circuits weren't soldered together, they were welded together to form modules like the one that you can see on the slide. So that sort of white thing that you can see, that's one of the modules that was in the computer. And if you look, there's these little pins running along the top of the modules, if you look really carefully, and those pins allowed the modules to kind of plug together. So 26 of those modules, there you can see them, 26 of those modules form the final computer. There's another picture of the tray with some modules inserted. And there's a picture of the other side. Now, all of those little blue lines you can see are little wires connecting the pins of all the modules together. So it was a really sort of intricate and complicated, it's called a backplane, and that sort of carries all the signals between the different modules. Now, the memory on the computer was very limited. The computer had 2,000 words of erasable memory. So that meant there were like 2,000 numbers that the computer could store. So if you imagine having some lined paper and you can write a number on each line, you've got 2,000 of those lines. So you can store 2,000 numbers. And the computer also had 36,000 words of fixed memory. And that's where the programs were stored. And what that means is you can have your computer can have 36,000 instructions that it can do. Now, neither of these numbers are very large by today's standards. Now, I love the fixed memory where the programs were stored, because I've shown that on the slide and I've really magnified it. Now, you might be able to see there's these little copper wires going through red rings. And sort of roughly speaking, if a copper wire went through a red ring, that was a binary 1, and if it didn't, that was a binary 0. So you have thousands of these tiny copper wires going through these even tinier rings, and that's how you made the program. So the software was literally woven together to form the fixed memory. Here's one of my favorite pictures from the Apollo program. This is an engineer at Raytheon, and she has a copy of the program put in front of her that's been made by the programmers, and she is weaving those tiny copper wires through those even tinier rings to turn that program into something that can be put into the computer and can fly on the spacecraft. And they used really experienced textile workers to do this. Now, who would have thought, you know, when you're sort of 20 years old and you decide you want a career in textiles, who would have thought that you would end up weaving the software for the Apollo spacecraft? It's just amazing. The computer was very featureful. This is a little bit technical. It had a real-time clock, so it was basically able to tell the time. That's good. It had interrupts, which are very important, and parity checking, which was used to sort of correct errors that might have occurred. And it had extensive input and output connectivity, and I'll explain a bit about that in a minute. It was also a bit quirky. It had a 15-bit word size. Now, what that means is the numbers that the computer can store are not very big. So it can store numbers up to about 30,000. And modern computers can store much larger numbers. It used ones complements for integers. What that means is you can have +0 and -0, which is sort of, again, very strange. It had no floating point numbers, so you couldn't have anything with a decimal point, but actually that's not too bad because you can just use whole numbers and scale them down. It had these sort of special memory locations. Let's not worry too much about that. Very limited memory, as we've seen, so it could only store 2,000 numbers and it could only store 36,000 instructions. And those instructions were quite unusual. So if you sort of took a modern day programmer like me and you said, here are the instructions that the Apollo guidance computer can run, someone like me would be sort of really confused because it's all really different to what I'm used to. So it would be like someone giving you a calculator, but rather than having like a plus key and a minus key and an equals key, you know, the keys have sort of got Russian on them, and they don't add numbers, they sort of, you know, multiply them and then divide by 2 or something strange like that. So just imagine being given a really weird calculator. That's how I would feel as a programmer if someone gave me an Apollo guidance computer to program. Now, inputs and outputs. So this device here is called the DISCI, and this is how the astronauts interact with the guidance computer. And you can see on the top right, it's got a display that can show some numbers. And it's got, on the top left-hand side, it's got some indicator lights, and it's got a keypad at the bottom where the astronauts can enter information. And I'll show you that being used later. And this was the main way that the astronauts interacted with the guidance computer. It used a verb-noun format for commands, and I'll explain that later. And there were also many other sort of human interface devices that were controlled by the computer. There were things like an 8-ball and lots of lights and also a hand controller. And again, I'll show you all of this later. The computer was able to send data back to Houston and receive data from Houston. And of course, if you're a computer in charge of a spacecraft, you have some very exciting input and output devices. For example, you have thrusters that can steer the spacecraft, and of course you have a massive rocket engine, and all of these things were controlled by the computer. Okay, so that's my introduction of the computer to you. Next, and this is possibly my favorite section, I'm going to show you how they landed on the moon, and I'm going to show you what the computer did. First, of course, we're going to need a spaceship. So here's our spaceship. And the first thing that we need is a big rocket engine. And we'll use that rocket engine to give ourselves lots of thrust, and we'll use that thrust to slow ourselves down, come out of orbit and land on the surface. We also need to be able to steer, and that's the job of these RCS thrusters. The main source of data for the computer is this device called the IMU. There's also a radar that can show you the height of the spacecraft above the surface. Next is the window. Now the window is very, very important, and I'll have a lot to say about the window later. And finally, in our spaceship sits the Apollo guidance computer, and it reads data from the IMU and the radar, and it controls the rocket engine and the RCS thrusters and all sorts of other devices. So there's our spaceship. I just want to talk about a couple of these devices in more detail. First, the RCS thrusters. I'm sure most people here will be very familiar with that. So on the four corners of the spacecraft are these little quads of 4 thrusters, and the computer can give little squirts of thrust through any of those thrusters, and by doing that the computer can steer the spacecraft in any direction that it wants to. And this is a completely sort of standard way of controlling any spacecraft. The other device you may not have seen is the IMU. The IMU has 3 concentric rings which can rotate around inside each other. And in the center of the IMU is the stable member. The stable member has gyroscopes on it that spin really fast, and that keeps the stable member completely rigid in space. So no matter how the spacecraft turns, the stable member stays completely in one orientation. And then there are sensors on those concentric rings that can measure how the spacecraft turns relative to the completely fixed stable member. So the IMU can tell you which direction the spacecraft is pointing, and it can tell you which way it's accelerating. And then the computer can do some simple maths to calculate the speed of the spacecraft and also the sort of the absolute position of the spacecraft in space. So the IMU is really important for the computer to know how fast it's going and where it is. Right, so there's our spaceship. Next, I need to condense sort of 100 hours of NASA training into 2 minutes and just give you a whistle-stop tour of how they landed on the moon before I then give you the full demo. So let me set the scene for you. We're coming into the mission at the point where the lunar module is in what's called the descent orbit. Now, I think this is a really misleading name because the descent orbit doesn't actually take you down to the surface. The lunar module could quite happily whiz around that descent orbit forever and ever. To land on the moon, we need to execute a series of maneuvers, starting from the lowest point in the orbit, and those maneuvers will take us down out of the orbit and onto the surface. Now, those maneuvers are the difficult bit of landing on the moon, and those maneuvers is what I'm going to talk about today. So I'm going to be talking about that red line on the diagram that takes us down to the surface. And that happens in 3 phases. The first phase is P63, the braking phase. Now, at the start of P63, the spacecraft is really high. It's 50,000 feet above the surface, and it's going really fast. And the aim of P63 is to slow the spacecraft down. So to do that, we point the big rocket engine out in front of us and we fire it, and that slows us down and brings us out of orbit. So that at the end of P63, we're a lot lower, we're 8,000 feet above the surface, and we're going a lot more slowly. The next phase is P64, the approach phase. The aim of P64 is for the astronauts and the computer to work together to fine-tune the landing site. Now, at the start of P64, the astronauts are basically on their back looking out towards, well, the sky, basically, if there was a sky on the moon. So the first thing we do at the start of P64 is we do that pitch over maneuver, and that gives the astronauts forward visibility so they can see where they're going. So during P64, the astronauts and the computer work together to fine-tune the landing site. And then we enter P66, the final phase. The aim of P66 is to touch down nice and gently, perfectly vertically, and without any side-to-side movement. So that's the 3 phases of the landing. P63, where we slow down and we lose most of our height. P64, the approach phase, where the astronauts and the computer work together to fine-tune the landing site. And then P66, the final phase, where we want to touch down in a nice and graceful manner and not break the spaceship. Okay, lovely. So that's the training over. Now I can give you the demo of the computer. Now, there's quite a lot of detail here because, you know, the MEXPA and Swinton Astronomical Society, of course, wants a nice, authentic demo of the computer being used. So I will definitely give that to you. But don't worry too much about the details. I just want you to kind of just sit back and just take in the awesomeness of this computer. And if some of the details pass you by, don't worry at all. You'll still be able to understand the rest of the talk. So off we go, let's rewind the clock. So we're coming into the mission and we're in the descent orbit and we're about 10 minutes before we're going to do those maneuvers that land us on the surface. Remember this thing, this is the disky, this is what the astronauts use. And the first thing they need to do is they need to load the landing software. So to do that, they type verb 37, which means please load this bit of code. And then they type in the number, which is 63. And when they do that, the computer switches to program 63. And the first thing the computer does is it shows verb 6, noun 61. Well, what does that mean? Well, that means the computer is telling the astronauts some information about the landing. So prior to this point, the computer has been programmed in with the landing site, and the computer has calculated exactly what time it needs to light the rocket engine in order to follow the right trajectory and land in the right place. And that's that second number on the disky that I've shown in the red box. So the computer is saying it's 10 minutes until we need to light the rocket engine. Okay, let's wind forward the clock a bit. It's now 1 minute 20 before we're going to start lighting the rocket engine. And even now, giving this presentation, I can feel myself getting excited. And the computer has an important message for the astronauts. So to indicate that, it lights up the key release light on the disky. And the astronauts can view that important message by pressing the key release button. And the message is verb 50, noun 18. Well, what on earth does that mean? Well, that is the computer asking permission to turn the spacecraft. Now, if you remember at the start of P63, we need the rocket engine pointing out in front of us, and the computer is asking permission to do that. Now, if the astronauts are happy for that to happen, they can press the proceed key on the disky. I've highlighted that in red. And the computer will then automatically maneuver the spacecraft into the correct orientation. The next thing the computer does is called ullage, and it fires some of those RCS thrusters and that settles the rocket fuel into the bottom of the fuel tanks to make sure that the rocket engine ignites cleanly first time. So they really did think of everything. Let me just take a drink of my coffee. Now wind forward the clock again. It's now 5 seconds before ignition, and the computer flashes verb 99, noun 62. Now, every Apollo astronaut can tell you what verb 99, noun 62 means. It means, are you sure you want to land on the moon? And the astronauts have 5 seconds to calmly reach over press the proceed key and secure their place in history. So let's do that. We press that proceed key. Now, just to remind you where we are, we're still in the descent orbit. We are now at the exact point that the computer has calculated we need to light that engine. And we've just authorized the computer to do that. We've got the spacecraft pointing in the right direction. We've settled the rocket fuel in the bottom of the fuel tanks. We are completely ready to go. And we know how this works, thanks to our training. It starts with P63, the braking phase. And the first thing the computer does is it lights the rocket engine, but at a really kind of weedy 10% thrust. I mean, what an anticlimax. What on earth is going on? And I have to say, this is my favorite bit of the whole software. And I was so sort of happy when I found out about it. So we're kind of firing this massive rocket engine at sort of no thrust at all. The computer is measuring to see whether that thrust causes the spacecraft to spin around. And if the computer notices that a spin is occurring, it will swivel the rocket engine to make sure that the thrust is going perfectly through the center of gravity, and that will stop the spinning. And after about 30 seconds of gently firing the engine and measuring the spin and swiveling the engine to sort of counteract any spin, the computer then ramps up the thrust to full thrust. And full thrust here is 94%. Well, that's a bit more like it. Now, this is not just a case of fire a massive rocket engine and hope for the best. Throughout the entire landing, the computer has 2 points in its mind, shown at the bottom of the slide here. The first one in green is the desired landing site. That's the landing site that's been programmed into the computer. That is where they've said they want to land. And the other one in blue is the projected landing site. And that's where the computer thinks it's going to land based on extrapolating its current trajectory. And throughout the entire landing, the computer wants to steer the spacecraft to try and move the projected landing site towards the desired landing site. Okay, lovely. Now, at the start of P63, the landing radar cannot see the surface. And to indicate that, the computer lights the altitude and velocity lights on the DSKY. So at the start of P63, because there's no landing radar, the only source of data we have is from the IMU. Now, the IMU is incredibly accurate, but it loses accuracy during accelerated flight. And of course, nothing says accelerated flight like having a massive rocket engine lit up in front of you. So that the altitude and velocity lights are illuminated, the computer is saying, I don't know exactly how high I am, and I don't know exactly how fast I'm going, because the only data I've got is from the IMU. Okay, so let's wind forward again. We're a bit lower now. We're still in P63, but we're a bit lower. At this point, the landing radar locks onto the surface of the moon, and it starts providing altitude information to the guidance computer. So that's the situation we were in. And then once the landing radar locks on, the computer clears those 2 lights from the DSKY. Now, the astronauts are waiting for this moment. They're waiting for those 2 lights to go out. And when they go out, the astronauts type in verb 6, noun 63. And that means, please show me the discrepancy between how high you thought you were based on the inaccurate data from the IMU and how high you actually are based on the much more accurate data from the landing radar. And the computer shows that information. And it was common at this point in the flight for there to be a 1,000 or 2,000 feet discrepancy between how high the computer thought it was and then how high it actually is based on the data from the radar. Now, when you're 40,000 feet above the surface, 1,000 feet here or there doesn't make much of a difference. But of course, as you get closer to the ground, you really want to be using the most accurate information you can. So what the astronauts do is they look at this data, they sort of make sure it looks sort of vaguely sane. And if they're happy, they do something called incorporating. So to incorporate, they type in verb 57, which means please incorporate the landing radar data. At that point, the landing radar data feeds into those guidance algorithms, and the guidance computer will then gradually correct the trajectory based on this more accurate information. So let me just show you with our picture. So the landing radar is locked onto the surface. The astronauts incorporate the more accurate data, and that has the effect of moving the projected landing site because the computer's in a different place to where it thought it was. And then, as always, the computer will then steer the spacecraft to move the projected landing site back towards where it's supposed to be landing. Great. Towards the end of P63, the computer automatically ramps down the thrust. And then we enter P64. And of course, we know the first thing that happens at the start of P64, we do that pitch over maneuver. So the computer does that for us. And the aim of P64 is for the astronauts and the computer to work together to fine-tune the landing site. The computer needs a really sophisticated way of showing the astronauts where they're going to land. Yes, it's the window. Now, the window has two axes marked on it like this. And during P64, the computer shows verb 6, noun 64. So let me show you how that works. That 5 that you can see on the disky means look 5 along the horizontal axis. And that 40 means look 40 up the vertical axis. And then Armstrong needs to imagine a red dot at that intersection. And that red dot is the computer saying that red dot that you can imagine out of the window, that is where you're going to land. It's very, very clever. What happens if Armstrong doesn't like the look of where the spaceship is going to land? Well, he's got a hand controller. And if he moves his hand controller, that moves the desired landing site. And then, as always, the computer will re-steer the spacecraft to move the projected landing site back towards the new desired landing site that Armstrong has done by moving his hand controller. And it was common during P64 for that imaginary red dot to move around the window, especially if Armstrong was changing the landing site with his hand controller. Now, during P64, the hand controller is connected to these sophisticated guidance algorithms. The hand controller moves the desired landing site. And then the guidance algorithms calculate how the spacecraft should be steered to get to that new desired landing site. And those steering commands are sent to the much sort of simpler attitude control software. And that attitude control software translates those steering commands into firing the different RCS thrusters. Now, when the spacecraft is above the landing site, Armstrong moves this pings mode switch from auto to attitude hold. And roughly speaking, that puts the computer P66. And then in P66, the hand controller is disconnected from the sophisticated guidance algorithms, and it's connected to the much lower level attitude control software. What does this mean? Well, it means that during P66, if Armstrong moves his hand controller, it directly steers the spacecraft. So it doesn't move the desired landing site, it directly steers the spaceship. So it's a much more direct relationship of control during P66. But I want to make the point that even in P66, there is still code running between Armstrong's hand controller and the thrusters. Finally, when we're really close to the ground, a big cloud of smoke and dust gets kicked up, and the astronauts can no longer see out of the window. So instead, they look inside the cockpit at two instruments. The first one is the 8-ball, and that tells you whether the spaceship is vertical. And the other one on the right is the cross-pointer display, and that tells you whether you have any side-to-side or forwards and backwards movement. And this is very similar to how an aircraft pilot would land in the fog. Finally, once we touch the surface, a blue light illuminates. The astronauts quickly shut down the engines and breathe a sigh of relief. So that's how you land on the moon, and that's my demonstration of the Apollo guidance computer. But what about those pesky program alarms? Well, a 1202 alarm was a very serious problem. In modern day terms, it's a bit like seeing that on your computer. Or if you're a bit more old school, something like that. Or worst of all, something like that. A 1202 alarm was a serious event. And the question of whether you abort or not was a very important one. If the astronauts had hit the abort button, then 4 pyrotechnic bolts holding the 2 halves of the spaceship together would have exploded, and a 5th pyrotechnic guillotine would have sliced through all of the cables connecting the 2 halves together. So you can sort of only abort once, if you know what I mean. And at that point, the half with the astronauts in it takes off back into orbit, and then Mike Collins in the command module has quite an important orbital mechanics problem to solve, because he's got to go and pick up his friends. So you could only abort once. It was technically non-trivial, and so when the 1202 alarm occurred, they had to decide very quickly whether it was safe to continue or whether they should sort of do this abort. And this is going to be the subject of the latter half of the presentation. So first, I'm going to talk a bit about how they made the software robust, and then we'll jump back into the cockpit and we'll go through the Apollo 11 landing, and I'll explain what caused those alarms and why it was safe to continue. First, though, a little bit about the software. Now, this is sort of a slightly drier and more sort of technical 10 minutes of the talk. So just sort of let me say what I've got to say, and then in 10 minutes time, we'll sort of leap back into the cockpit and we'll have fun for the last 10 or 15 minutes. So the software that ran in the lunar module was called Luminary. And it was very sophisticated, wide-ranging software. And it controlled all phases of the lunar module's mission. So it got the lunar module into the descent orbit. It landed on the moon. That's the bit I was talking about. It controlled taking off again from the surface. And it also controlled rendezvousing back with the command module. And this software was doing all sorts of things. It was controlling the RCS thrusters to do the steering. It was reading information from the diski. It was controlling the 8-ball and the cross-pointer display. It was sending data to and from Houston. It was doing all sorts of different things. So it ran a simple real-time operating system that they wrote from scratch. And of course, the source for Luminary is available on GitHub. And this software used 6 design principles to make it robust, and I'll just go through those very quickly. The first one used a high-level language. So the way that you programmed the Apollo guidance computer was very primitive and unusual. If you remember, I was talking about that earlier, and I said it's a bit like being given a calculator where all the buttons are in Russian and they do things that you're not used to. And also, the numbers that the computer could store were very small, and that didn't give you enough accuracy for the really sophisticated guidance algorithms. So their solution to this was to write something called the interpreter. And the interpreter gave you a much more sophisticated set of instructions. It gave you things like matrices and vectors, which are really useful for physics calculations. And it also gave you things like being able to index into an array, and it gave you a stack, which is useful for manipulating values and calling functions. I don't know if anyone's ever used one of those, it's quite old school now, but those HP, was it the HP 96 calculators that where you typed in the two numbers and then you typed the operation. That also used a stack, and those calculators used to be really popular with engineers because a stack is a really useful way of doing complex calculations. The interpreter also gave you double and triple precision integers, so it gave you numbers that were a lot bigger, and that gave you much more accuracy for your calculations. And it also made it easier to write correct code, but the downside of the interpreter was it ran really slowly. So the final software was a mixture of the two. The really time-critical stuff was written in the sort of awkward low-level instructions, and then the complex guidance algorithms were written in the interpreter. Number 2, divide your system into jobs. The software was divided into jobs where each job did a particular bit of the system. So, for example, there was a job called readax, and readax read data from the IMU accelerometers and calculated the position and the velocity of the spacecraft. There was a whole suite of jobs that controlled the digital autopilot, and that's basically the thing I was demoing a few minutes ago. There was a really charmingly named job called Pinball, and Pinball was responsible for updating all the numbers on the diski. And there are lots of other jobs that I don't have time to describe here. And each job had a small area of memory called a core set. And a core set was sort of like a place where you could write down intermediate results in your calculations. So it was like having a sheet of A4 paper where you're doing some calculations and you can write some numbers down on it. And in particular, you could store 7 numbers that were sort of useful for your particular job. And there was only enough memory to have 7 of these jobs. So it's sort of like having 7 pieces of A4 paper. So you can have 7 different jobs. You can give each job a different piece of paper, but there's no room for an 8th job because there's not enough paper. Number 3, restart on failure. So it's a sad fact of life, speaking as a software engineer, that all software will encounter failures. I don't mean bugs where the programmer was lazy or misunderstood the specification. Those things would be caught much earlier in testing. I'm talking about 1 in a million, once in a blue moon things that might happen. And those sort of once in a blue moon events can cause the software to do unusual things that people haven't thought of. And if software has failed, it can't be trusted to recover itself. It's failed, so all bets are off. So instead, you restart the bit of software that's failed. And the hope is if you restart it, whatever once in a blue moon thing caused it to fail, that will have gone away. The software can have another go and hopefully recover from the error. And the AGC provided various levels of restart. You could restart just the failed job or a group of jobs. You could restart all of the software, but keep important information like where you are and how fast you're going intact, and that was called a PUDO. Or you could restart the entire hardware, just absolutely everything, and that was called a fresh start. Okay, we're halfway through. Thanks for bearing with me on this one. Checkpoint your good state. So I was talking about restarting software that's failed. And that's great, but the problem is you lose your state. So for example, if you imagine being on your PC and you've got a Word document open, if you restart your computer, you lose that document. So what you want to do is you want to save that document every so often when you kind of reach, you sort of finish your paragraph, perhaps you save your document. And the Apollo guidance computer used a similar mechanism. It had a thing called checkpoints, and that means when a particular job gets to a sort of a known good state, it can kind of save that for later. And if the job gets restarted, it can recover from that saved information. For example, if you're the job that's reading data from the IMU and calculating the position and the speed of the spacecraft, your job will sort of read all the data from the IMU. It will do loads and loads of calculations, and then at the end, it will save that information to checkpoint. And that means that if the job reaches the end, then the checkpoint gets updated. But if it crashes halfway through, the checkpoint doesn't get changed. Number 5, hardware monitors the software. This is the most technical one. So the AGC used something called cooperative multitasking. And this meant that each job had to, every so often, it had to check to see whether another job was being run. So it's sort of like really polite software, really polite code. And every so often, the code sort of asks around and says, is there any other code that wants to run? Is there any other job that wants to run? So it's just the most polite code you've ever seen. Very, very British, you could say. And in the case of the computer, the way that you checked was every so often in your code, you had to write a special instruction that checked this thing called new job. And if there was a number, a particular number in new job, that meant there was another job that was waiting to run. And so at that point, your code would stop running and it would hand control over to whichever job was waiting. Now you might say, well, isn't this a bit rubbish? Because you have to explicitly write those checks. But actually, all of the software was written by one team. And so you just said to all of your engineers, you need to make sure when you write your code, you need to make sure that every so often you check this new job variable. Basically, all the engineers have to write this polite code. Now you might say, well, what happens if for whatever reason that maybe the code gets sort of stuck in an infinite loop, and it for whatever reason it doesn't check this variable, and in that case the hardware intervenes. So it's almost like having a maybe imagine like a strict head teacher, and the head teacher is sort of making sure that everyone is being polite, making sure that every so often everyone is checking to see whether is checking to make sure everyone's polite. Or in the case of the computer is checking to make sure that all the jobs every so often are doing this check. And if the hardware notices that a job hasn't done the check, then the hardware will trigger a restart. So using my head teacher analogy, if the head teacher notices that a particular pupil is not being polite, the head teacher says, right, playtime's over, everybody go inside, we're going to start again. Number 6, send telemetry about your system. So the DISCI, it was great for what it was, but it could only show you 3 numbers and a few lights. So to get around this, the computer, every so often, it sent information about its internal state back to Houston. And this was about 100 important numbers, for example, like position and speed and what program you're running and where you think you're landing. And Houston had a whole team of people in mission control, and they were completely devoted to the guidance computer. So they would, this team would stare at this telemetry coming from the spaceship, and they would make sure that the guidance computer was working properly. So those are my 6 design principles. Use a high-level language so that these complex algorithms are easier to write. Divide your system into jobs where each job does one thing. If a job fails, then you restart it. And the hope is that whatever sort of once in a blue moon event triggered the failure will have gone away. Checkpoint your good state so that when after a restart, you can pick up from where you left off. Hardware monitors the software to make sure that everything is behaving nicely, and send telemetry about your system back to a team of experts who can make sure the system is working correctly. Lovely. So in the last 10 minutes, I'm going to walk you through the Apollo 11 landing, and I will show you those program alarms and how the system recovered. And for me, there's some questions here. So what caused these 1202 alarms? Was the spacecraft in danger? And importantly, why did the alarm start halfway through the landing rather than at the start of the landing? So it would have been really helpful if the alarms had happened a lot earlier, for example, in the descent orbit, because that's a much less critical phase. Why did the alarm start halfway through the landing? And finally, why did the alarm stop after Armstrong seized manual control? At the end of this section, you will have answers to all of these questions, and you can impress all of your friends. First, I've lied to you. There was an extra radar on the spaceship called the rendezvous radar. Now, the rendezvous radar was basically useless during the landing, but when you were taking off again, the rendezvous radar was used to find the command module in orbit. Now, during the landing, the guidance computer is reading all this data from the radar and the IMU. It's controlling the rocket engine and the thrusters. It's running all of this code. It's a very computationally intensive part of the mission, and it puts the computer under an 80% load. So it's sort of quite heavily loaded. And the rendezvous radar had a hardware bug. And if you were really, really, really unlucky, like 1 in a million type chance, you could trigger this bug. And of course, landing on the moon, I'd say, is a 1 in a million type thing. And so, of course, during Apollo 11, during the landing, they were really unlucky and they triggered this bug. And the bug caused the radar to send basically a stream of zeros to the computer. So the radar had this bug. They were really unlucky and they triggered this bug, and that caused the radar to send this stream of zeros. And that put the computer under an additional 15% load because the computer had to handle all of this extra input. So if you imagine having a friend who sort of comes up behind you and taps you on the shoulder, and then you look around and they just smile at you and they have nothing to say. And if you imagine that they keep tapping you on the shoulder, that takes up some of your time. You're sort of preoccupied with this annoying friend. And it's the same with the rendezvous radar. The rendezvous radar is constantly tapping the computer, but the rendezvous radar has no useful information. However, 80 plus 15 is 95%. So actually, this is fine. Even though they trigger this hardware bug, the computer can just about cope. And this meant that at the start of the landing, they didn't notice there was any problem, even though they triggered this bug. They just didn't notice that there was any problem. So what changed? Well, what changed was Buzz Aldrin. And Buzz Aldrin was obviously really excited to be landing on the moon, as I would be, and I think as anyone here would be. And Buzz typed in verb 16, noun 68. Now, this is a completely legitimate thing for Buzz to do. He'd done it in training thousands of times before. Buzz had never had a problem with this before. And what does verb 16, noun 68 tell you? Well, it means, please show me some information about the landing, and please constantly update the display with that information. Okay, well, that all sounds fine. Well, what's the problem? Well, the problem is this. When Buzz enters verb 16, noun 68, that starts a new bit of code because we need to constantly recalculate those numbers and update the DSKY with that information that Buzz has asked for. And that puts the computer under an extra 10% load. Now, normally, again, that would be fine because 80 plus 10 is 90%. And that was, this configuration had been done in training before. But when you then add in the extra load from the hardware bug, then you have a problem, because now the computer is overloaded. It's only slightly overloaded, but it is overloaded. And it falls over in slow motion like this. The jobs slowly pile up. And if you remember earlier, I said there was enough memory to have 7 jobs on the go. But the computer can't quite run them quickly enough. So when the 8th job comes along and says, well, I'd like a piece of paper to show my working, please, there's a problem. There's no memory for that job. And that triggers, when my PowerPoint works, that triggers the 12:02 alarm, which literally means there's no memory for this job. Okay, so what does Buzz see? Well, he's typed in verb 16, noun 68, and then a couple of seconds later, he sees 2 lights that you never want to see when you're landing on the moon. The first is the program alarm light, followed rapidly by the restart light. This is not good. Buzz needs to figure out what this alarm is. To figure that out, he types in verb 5, which means noun 9, which means please show me the program alarm that just happened. And the computer replies, and it says that a 12:02 alarm occurred, and the 3 is the restart type. So the 3 is sort of how the computer recovered. Okay. So there's where we were, and then Buzz types in his verb 16, noun 68. The program alarm happens, but the computer recovers. How does that work? Well, the computer restarts various jobs, but crucially, it does not restart Buzz's, the bit of code that's running Buzz's 1668 job, because it's considered not important enough. And that removes the extra load from the computer, and it allows it to recover. So that explains the first program alarm. But there were 5 in total, so what about the second? Well, Buzz, of course, I think is a bit annoyed because he's typed in verb 16, noun 68, and all he gets is this pesky program alarm. So he reaches over and he types verb 16, noun 68 again. Sure enough, that starts that extra bit of code, which again puts the computer under an extra 10% load. Once again, all of the jobs pile up. When we get to the 8th job, there's no memory, and that again triggers the program alarm. Once again, the computer restarts various jobs. It doesn't restart Buzz's 1668 job because it's considered not important enough. That removes the extra load from the system, and the system recovers. So that's the second program alarm. And there's this moment in the mission recording where the penny drops, and Buzz, he says, it seems to happen when we have a 1668 come up. So Buzz correctly realizes that this, when he types in verb 16, noun 68, that causes the program alarm. He doesn't know why, but he realizes the connection. So I can assure you from this moment on, Buzz is sat on his hands. He never types in verb 16, noun 68 again, because he cannot risk causing another program alarm. So the flight continues for a while. And let me just summarize those 2 alarms. So the cause of the program alarm, we had that unexpected load from the hardware bug, combined with Buzz typing in the verb 16, noun 68. Was the spacecraft in danger? No, the spacecraft kept on flying. It was absolutely fine, even though these alarms happened. Why did they start halfway through the landing? Well, of course, the hardware bug was triggered right at the start, but the straw that broke the camel's back was Buzz entering this verb 16, noun 68. So that's why they only saw it halfway through. Okay, but there were 3 more program alarms. What caused them? Was it Buzz entering verb 16, noun 68? No, it absolutely wasn't. There was no way that Buzz was going to enter verb 16, noun 68 again. No, the last 3 alarms happened during P64. If you remember, that is the astronauts fine-tuning the landing site. The computer is calculating that imaginary red dot. It's just naturally more computationally intensive. The load during P64 is just higher, and that combined with the hardware bug just naturally overloads the computer without Buzz doing anything. And that's the cause of the last 3 program alarms. But once again, the computer is able to recover by restarting various bits of the job, jobs in the system. But there's one more mystery. Why was it that when Armstrong seized manual control, why were there no more alarms? Well, we know what happened. Armstrong didn't seize manual control at all. He entered P66, which, if you remember, connects the hand controller to the much simpler steering software, which naturally just is less computationally intensive. So when Armstrong moves to P66, he doesn't know that this is going to happen, but it would just naturally reduces the load that's on the computer. So the cause of the program alarms, for alarms 3, 4, and 5, it was just the extra load from P64. Buzz didn't need to do anything to trigger the last 3 alarms. And why did the alarms stop after Armstrong seized manual control? Well, actually, he just entered P66, which just naturally reduced the load that was on the system. And then just wrapping up in the last minute or 2. Let's go back to our design principles. How did they help? Restart on failure. The computer automatically recovered from the high load situations by restarting bits of the system. And that meant, for example, that Buzz's Buzz's 1668 job, it wasn't restarted, and that helped the system recover. And the fact that the system was divided into jobs meant that the really important bits of the software kept on running the whole time. Checkpoint your good state. That meant that after a restart, the software would sort of look in its checkpoint and it would say, what am I doing? And its checkpoint would say, you're landing on the moon, you know, get on with it. This is where you are and this is how fast you're going. So even though there were restarts, the software was able to use the checkpoint to pick up from where it left off. And finally, send telemetry. So I hope even diagnosing the program alarm on the DISCI was hard. If you remember, Buzz had to type in verb 5 now 9, and then the DISCI just showed a number. But because the computer was sending telemetry back to Houston, that gave Houston the confidence and the authority to give Armstrong the go to continue. I'm sure everyone here will appreciate that Apollo was the confluence of so many bright and talented engineers, but I want to pick out 2 people, 3 people in fact. The first is Steve Bales. He accepted the NASA Group Achievement Award on behalf of the entire Apollo 11 mission operations team. This is a much more prestigious award than you would think based on the name. And in the words of Nixon, this is the young man when the computer seemed to be confused and when he could have said stop or when he could have said wait, said go. It was Steve Bales who was on the desk in mission control. He gave the go to continue. Equally importantly, though, was Jack Garman. He was in the back room and he, more than anyone else, understood the exact meaning of these program alarms. It was he who understood it was safe to continue, and he was talking to Steve Bales, and he was saying to Steve Bales, yes, it's safe to continue. And finally, Margaret Hamilton. She led the team at MIT who developed this amazing software. And she finally received the US Presidential Medal of Freedom in 2016. That's the highest civilian award you can get in the United States. And that was for her entire career of developing fault-tolerant systems. So to close, These pioneering techniques that I've spoken about form the basis of all sorts of robust software today, including the software that I work on. And although it's not quite as cool as landing on the moon, I do love my job and I wouldn't change it for the world. So with that, people are very welcome to contact me if anyone has any feedback or any questions. There's an excellent recording of this talk already online, which you can find. And with that, I'm very happy to take any questions if anyone has any.
Thank you very much, Robert. That was a fascinating talk. Before we go to any questions, can you stop sharing your screen, please?
Of course.
And then we'll go back to gallery view, and so we can see as many people as possible. As always, ladies and gentlemen, it's question time. And as you're thinking up your questions, can I ask you to put a digital hand up, please, if you can, or wave at me furiously, but give me a few moments. Rather than starting off, I can see that Tony Morris is desperate to ask a question. Tony, can you unmute yourself?
Can you hear me, Paul?
Excellent. I can hear you, Tony. Off you go.
Press the right button this week. Okay, a question then. For excellent presentation on the software and what the astronauts had to do. But there's a really interesting YouTube channel called Curious Mark, and they've been rebuilding the guidance computers, both hardware and software. I wonder if anybody's got any comments on that. Has anybody been watching it? Has Robert been involved in their work?
Robert,
so I know a bit about it, but before I say anything, has anyone else seen that channel?
No, getting lots of shakings of heads. No thumbs up.
Okay. So let me say a bit about. So I've not been directly involved, although I am in touch with some of the people involved. Real Apollo guidance computers are incredibly rare. So there's obviously a few of them on the moon. There's a few of them that have actually, are they only on the moon? No, that makes no sense. There were none on the moon, obviously. Quite a few have burnt up in. Oh, there were.
Yeah, because
well, anyway,
the LEMs recrashed into the moon, didn't they? After they went back onto their CSM, the LEM was crashed into the moon to test out the seismology units.
Yeah.
Either way, those computers are certainly not on planet Earth. So real Apollo guidance computers are very rare. And so there was a project, there was one that got bought as part of like a ton of scrap from NASA. And there was a painstaking project to restore it. And it's, to be honest, it's probably the only computer, the only working computer that's ever going to exist on the Earth.
Right. I'm surprised that they haven't tried to scavenge one from the returned modules.
Well, the trouble was a lot of that stuff was just chucked away.
Right. Okay.
And yeah, so they are very hard to come by, these guidance computers. I mean, only a few hundred were ever built in the first place as well.
Right. Okay.
There was
okay, Tony.
On Paul, there was one that came up on auction. It went for just under $300,000.
Right.
So
okay,
as Robert says, there wasn't many of them.
No.
And do you know what? When that auction, if there was ever a time I wanted $300,000, it was when I saw that computer being auctioned.
Right. Okay. Another question. Jan and Dave.
Thank you. Robert, firstly, fabulous talk. You're the first IT person that I've ever understood. So thank you for that. I do have a question though. Did the astronauts have a clipboard or something with all those codes on, or did they have to remember them all before takeoff?
Yeah, do you know, and you're absolutely right, because all of this, like, you know, verb 6, noun 61, it all sounds like gobbledygook to us. So, but believe me, there is actually quite a lot of method to that madness. Yes, the astronauts did have those things written down. They were written down in their checklists, but actually those numbers would very quickly have become second nature to them, because they were just used so often for all bits of the mission. And so if you listen, for example, to recordings of people talking in mission control or the astronauts talking, they don't say things like, they don't say things like, let's recalibrate the IMU, or let's get the rocket engine ready. They say, let's do a verb 54, or let's do a verb 57. So very quickly, those numbers almost became part of the technical phraseology.
Thank you.
I've got to say, if you haven't caught up with it, the BBC for the anniversary, the recent big anniversary of Apollo 11, they did a podcast called 13 Minutes to the Moon. And it is, it's 13 minutes to the moon, and it's concentrating on the last 13 minutes of descent, and it takes you through the whole story of those last 13 minutes. It's an excellent program. I would recommend it to anybody. I have one question before we open it up. The landing programs, P63, 64, 66, what's P65? Or is there a P65?
Yeah, of course there's a P65. So so we have P63, P64. Both of those is basically the computer doing most stuff automatically. P65 was actually the computer could land itself automatically right the way down to the surface. And so the P65 was the final bit of the automatic landing. But the astronauts always had the option of switching to P66, which gave them much more control over the landing. And the astronauts, I think in every Apollo mission, they always switched to P66 before P65 had a chance to kick in. But in theory, the computer could land itself completely automatically, and that was the final bit of that was P65.
Okay, thank you. Catherine, can you unmute yourself, please?
Yes, I've unmuted myself. This was cutting edge technology when it was being built, and presumably there must be a level of risk involved. For things like doing the dynamics calculations, that must be pretty difficult. So did they have like an analog computer being developed in the background in case they couldn't get the digital computer to work?
So that's such a great question, and I've never been asked that before, so it's great to be able to answer. No, that's fine. So in when did the Apollo program start? It was either 60 or 61, but right at the start, when they commissioned the Apollo guidance computer, they sort of said, oh, we just need a simple computer, it doesn't need to do many things. And then sometime around, I think it was 1964, NASA changed the requirements and they said, actually, we want the computer to have an entire autopilot implemented. And that was basically the kind of complicated dynamic stuff. So all of that sort of got thrown into the requirements a few years into the program. There was no analog computer backup. Basically, controlling the spacecraft would have been more or less impossible without the computer. So even if they did have an analog computer to do the calculations, there's no way they could have then controlled the spacecraft just by humans. Basically, humans are not quick enough to do the kind of control.
Thank you.
Okay, Catherine. Roy Gunson, please.
I was wondering, it's well known that the Russians were not that far behind the Americans. I mean, they even got to the stage of building their own lunar lander. Were they developing computer technology on similar lines?
Another great and unique question. So the wonderful thing about the Apollo guidance computer, as with loads of things Apollo related, is that there is literally hundreds of thousands of pages of technical documentation in the public domain. For the Russian space program, there is almost nothing. So I have no idea if the Russians has an equivalent computer, because I think so little of that is in the public domain, certainly not that I've found. And that's such a contrast to the treasure trove of information from NASA about their guidance computer and loads of things Apollo related.
Okay, Roy. Tony Morris.
Just come back information for Catherine and Robert. So Hewlett-Packard used to advertise in the late 60s, early 70s that the Apollo missions actually flew with their calculators. So the astronauts had got Hewlett-Packard calculators to back up. I don't know what model it was, but that's what Hewlett-Packard used to say.
Okay, thanks for that, Tony. Okay, Peter Lloyd.
Yeah, thank you, Robert. Can I just go back to P65? I'm wondering how P65 was tested.
I mean, to be fair, you could also wonder how P63, P64, and P66 were tested, because the only way you really test it is by landing on the moon. All of the software, including P65, they had lots of digital simulations. So they basically had a physics simulation of the spacecraft and the moon, and they sort of plugged on Earth. They plugged the Apollo guidance computer into this physics simulation, and they tested all of the software, including P65, against that physics simulation.
It's just that I sort of ended my career testing software, and the P65 would have been so crucial to the safety of the astronauts. I don't blame them for not using it.
I think that's a fair comment. I also think so there's a really interesting human side to all of this. So in the early 60s, pilots like Armstrong were actually incredibly skeptical that a computer could do any of the flying. And then Armstrong had his mind changed after a couple of very heart-racing test flights they had a high altitude plane. Anyway, Armstrong had various experiences that persuaded him that having a computer do some of the spacecraft control was actually really useful. But there was always this almost tension between humans or the astronauts wanting to be sort of manually controlling the spacecraft versus having completely automated control. What point am I making here? And I think the kind of sweet spot that they found was that for most of the landing, the computer is better at doing orbital mechanics than the astronauts, but for the last phase of the landing, the astronauts are better at doing it. So that was another reason why the astronauts always entered P66, because frankly, for the last bit of the landing, the astronauts were just better at it.
I can believe that. Yes, thank you.
Okay, Peter. John Leach.
Hi, Robert. That was a fascinating talk. I've got a history of IT. My first computer was a NASCOM 1, which I built in kit in 1978, followed by a ZX81 from Sinclair. But, you know, to think that that was before then is absolutely awesome. Ever a respect for them. And an excellent talk. Wonderful.
Thank you, John. Just a follow-up question to that, and that was when was the design for the computer actually fixed? Because I'm asking that question because a lot of hardware is fixed long before the mission. And
yeah,
and so 66 was the Apollo 1 fire. They must have had a flight computer in that machine there. And then the last, presumably, the last mission it was used on was the Apollo Soyuz in, somebody might need to correct me on this if I'm wrong, 75?
feels about right.
Yeah, so we've got a bit of kit there that's flying for a long time. And you talked about 64. So when was the design actually fixed?
Don't quote me on this, but the hardware design was fixed around about 66, 67. In the early Apollo missions, so that's Apollo 1, and then there were various Apollo missions that just stayed in Earth orbit. For those missions, they used an earlier version of the design that was actually quite different. But the final design in terms of spacecraft that flew to the moon was finalized, yeah, around about 66, 67. Now, if you remember, I showed you that the computer was made out of these modules, and then the modules were connected with that backplane. And you might remember that picture with all the little blue lines that made up the backplane. It was actually quite easy to change the wiring on the backplane. So it was quite easy to do some modifications because you could just sort of tweak the wiring without having to rebuild all the modules. So there was some flexibility, but I would say the hardware design was more or less finalized in 66, 67.
Right.
By the way, these are great questions that people are asking, so please keep them coming.
Okay. Hold on to your seat. Gary Goldthorpe.
Hi,
good evening, Gary.
Good evening. Hi, a couple of questions. I presume, well, one's an assumption. I presume they fixed the rendezvous radar before Apollo 12, or did they have another method of dealing with the errors? And the second one is, how did they cope with the mountains on the moon? Because some of those are thousands of feet high.
Fantastic, fantastic. So I was lucky enough to speak to some of the engineers sort of actually involved in this project, and I specifically asked them about, did you fix the rendezvous radar? The answer is as follows. During the landing, you know, as the landing was unfolding, they knew there was a problem. They knew the computer was overloaded, but they didn't know why. But you can absolutely bet that as soon as Armstrong touched down on the surface, every engineer involved was phoned up, and they were told, we need an answer to this basically before they take off again, because we need to know if the computer's going to work during the takeoff. And over the ensuing hours and days, they were able to look at the telemetry and understand that it was the rendezvous radar causing the problem. Now, they actually knew about this hardware bug, but the Apollo program was very pressured, lots of time constraints. And they basically said, way back in 66, 67, they basically said, oh, hopefully we'll never trigger this bug. We've got much more important things to worry about. However, once it happened on Apollo 11, I think, the approach changed. So during subsequent Apollo missions, you could work around it by putting a particular switch into a different position. So they made sure that in the checklists for subsequent Apollo missions, it says in the checklist, it's really, really important during the landing that you put this switch in this different position. I'm also told that there was also a software fix, but I've not confirmed that. your second question, just remind me what that was.
How did they cope with the moons on the
the
mountains on the moon?
Yeah. So mountains on the moon was a major headache because, if you imagine you've got your sort of heavily undulating surface, and you've got your spacecraft, and you've got the radar measuring your height, and so the undulating surface causes your radar measurements to vary quite a lot. Now, during Apollo, for the Apollo 11 software, they basically they sort of modified the calculations to sort of smooth out these undulations caused by the mountains, and that basically is equivalent to them sort of almost like averaging out the mountains and pretending the surface was smooth. But the problem with that, of course, is that because you're pretending the surface is smooth, even though it isn't, it introduces inaccuracy into your trajectory. So for subsequent Apollo missions, they programmed a very simple terrain model of the moon into the computer, so that in subsequent missions, the computer was able to correct the radar data for the mountains that they knew were there.
That was impressive, in 36 kilobytes.
Yeah, tell me about it.
Okay, Gary.
Yep. Oh yes. Yep.
I'm going to ask for one more question. I'm looking around for one more question because I think we've worked Robert really hard this evening. And go on, last question to Tony Morris.
Just something for Robert. So I don't know if there's any other people on this Zoom call that have actually wired up threaded cores. So you know the core memory that you used. Well, the early versions of electronic telephone exchanges use a larger version of that. So sometimes I was involved in doing the threading, and that was quite interesting when you got it wrong.
I've got. Go on, Robert.
I've got a big. I've got a. It's funny you should mention that. So I've got a big tin of those magnetic cores that have been sent to me, and at some point, probably when I retire, I'm going to have a go at threading those cores together to form the memory, if my eyes are still good enough by then.
Robert, thank you for an excellent talk, and thank you for all your very knowledgeable answers as well to all our questions. Ladies and gentlemen, can we give Robert a huge Max for Swinton Astronomical Society? Thank you. Thank you very much, Robert.
Thank you.